Example 5.2. Figure 5.4 shows a small magnetized needle P placed at a point O. The arrow shows the direction of its magnetic moment. The other arrow shows different position and orientation of magnetic moment of another identical magnetized needle Q. In which configuration the system is not in equilibrium? In which configuration is the system in stable and unstable equilibrium? Last part, which configuration corresponds to the lowest potential energy among all the configurations? Okay. Now, first part is at point B. What is this point B? Magnetized needle is kept here, point B. First, we will draw the magnetic field lines due to magnetized needle B. That is, magnetized needle, magnetic field is always from north towards south, right? And it goes away from north, coming towards south. This is the magnetic field lines produced due to magnetized needle P. Now we'll come to the question. In which configuration the system is not in equilibrium? What do you mean by equilibrium? What is the formula? Okay, stable equilibrium, there is minimum potential energy. Unstable equilibrium means maximum potential energy. What's the formula for potential energy? Stable one, right? Okay. Formula for potential energy equal to minus of m dot b. What is m? Magnetic dipole moment. B is the magnetic field. Theta is angle between them. So potential energy formula minus mb cos theta. Now, stable equilibrium, minimum potential energy. Minimum potential energy means you should be positive. That is, magnetic moments, minimum means, sorry, you should be negative, minus value. That is, magnetic moment M is parallel to magnetic field. When both are parallel, theta becomes 0, energy becomes minus mb. That is the minimum energy. Stable equilibrium, there theta anti-parallel. So what is theta? Theta is 180. Cos 180 equal to minus 1. So energy becomes plus mb. So unstable equilibrium plus mb, stable equilibrium minus mb. In other words, stable equilibrium minimum potential energy and unstable equilibrium maximum potential energy. Okay. Now we start the question. I hope these 2 points clear. Keep these 2 points in the mind. First point, in which configuration the system is not in equilibrium? Not in equilibrium means not in stable equilibrium, not in unstable equilibrium. And okay, stable equilibrium means what? Stable equilibrium, minimum potential energy. In other words, M and B are parallel. Okay. Magnetic field lines are shown. Now, if you come to the Q6, P and Q6, these are in the same line, so we can take it as parallel. So, magnetic moments are parallel in Q6. Then, what about Q3? How it is parallel? Yes. Q3, don't refer this one. You see the field lines here, right? Field lines is coming downward. And Q3 is also downward. Q3 and field lines are in the same direction. For Q6, what we observed, it is along the same axis. So Q6 easily you can find out. But Q3, if you observe like this, it looks opposite, but you have to refer the field lines. P field lines is coming downward. Field lines is coming downward. Q3 is kept here. Now compare the arrow mark of Q3 with this arrow mark. Both are same, right? That is, both are in the same direction. So Q6 and Q3 both are parallel. Okay. Next, unstable. Unstable means they should be anti-parallel, opposite to each other. Okay, opposite to each other, Q5. Q5 and Q4. Q4 is here. Yes, it's easily we can make out this is upward, this is downward. So Q4 is clear. What about Q5? It looks here same, but what I told you have to observe with the magnetic field lines. Magnetic field is downward, but Q5 is upward. I repeat, magnetic field line is like this. It is going downward, but Q5 is upward. They are opposite to each other. Therefore, unstable equilibrium is at Q5 as well as Q4. Okay. Next point is not in equilibrium. What do you mean by not in equilibrium? Theta is not equal to 0. Theta is not equal to 180. It may be 90 other than these two angles. Okay. This point over. Easily we can make out. See this one. If you are comparing with the field line, it is perpendicular to the Q, perpendicular to P. That is angle between these two is so this is not in equilibrium. Similarly, Q2 is also not in equilibrium. Okay, next. Okay, now we'll go for the part C. Which configuration corresponds to lowest potential energy? What's the value of lowest potential energy? Lowest potential energy minus MV. Okay, but here dipoles are lowest potential energy means dipoles are parallel. Correct? Theta equal to 0. Alignment is perfect. Now, parallel in two conditions, Q6 as well as Q3. Where is your Q6? Here. Where is your Q3? Here. These two cases, what we have given, stable equilibrium, both are parallel. Q6 and Q3, out of these two, in which case energy is minimum? How to find minimum energy? There is, okay. For that, you have to consider this formula. Magnetic field along the axial line is given by mu 0 by 4 pi 2m r cube. Along the equatorial line is given by mu 0 4 pi m by r cube. Means, along the axial line, magnetic field is more. Along the equatorial line, magnetic field is less. Okay, magnetic field is more along the axial line. Now come to this one. Where is our Q6? Q6 is along the axial line. Q3 is along the equatorial line. हमको minimum potential energy means minus m dot b. So magnetic field is more, energy is less. M is constant. So magnetic field is more along the axial line, along the axial line. So Q6 is along the axial line. Therefore, even though it is stable equilibrium in two position, energy is minimum, energy is lowest, that is along Q6. Lowest potential energy is along Q6, that is dipoles are parallel. Q6 energy. Q6 is the axial line where B value is more than equilibrium. Actually, energy is, B value is negative, more. But if you substitute here, it becomes more negative means minimum. So Q6 potential energy is minimum.